well, first of all, thanking the organizers for giving me the opportunity to talk here and actually in this particular event. I guess, I met Frank probably either in Toronto at the Simple Theory meeting at the Fields Institute, or maybe at the Logic Colloquium in Barcelona a long time ago. I think this was the first time that I actually met him, but I didn't get to interact with him much until I was a postdoc, and then eventually I ended up in Lyon for 12 years overall. And I think what's most amazing about, at least my experience with Frank, is that he's been very welcoming. Privately, I felt like I was a member of the household. I was able to abuse his hospitality at many levels, and he never complained. He also never seemed to complain about me butchering his language when we were doing mathematics. He seems to be a very patient person, or he does it in a different way to release the pressure. So I always felt very at ease. Right. I must say, so I don't know if you've seen, it's a very indie film. It's called Gremlins. Okay, it's a very alternative movie, right? So there are these lovely creatures. Well, one, okay? Lovely. Lovely maybe is not the adjective that I will use to talk about Frank, but, and probably he also doesn't sing in the dark, I guess, I don't know. But I mean, so anyway, he's very welcoming, he's very lovely, he's very patient. I had the opportunities to do amazing mathematics, or actually to be part of some amazing proofs, despite my frustration for not understanding many of these steps. And the reason why I'm talking about gremlins is actually, like these animals are lovely, but then somehow if you feed them, they just become... After midnight. Yes, after midnight, of course, sorry, yes. So then they become a different person, and you cannot really relate these two people, right? So if... Huh? Yes, so that is true. So he doesn't get fed after midnight because of that reason also, but... So if you've ever experienced Frank on a bike or on a snowboard or on skis somehow, it's also quite difficult to relate these two people. Somehow there is this kind of crazy Enzo Fittipaldi who thinks somehow, he's going to be stopped by the police because of going over the high-speed limit on a bike, right? Right, so overall, thank you, Sean. Okay, so yes, and I would like to, before I get emotional, I would like to report actually on work done with Daniel Palestini. Maybe hopefully, if I manage, we'll get to see some ideas from which already appeared in Anand's talk, and then somehow we'll try to see how to. And also some of the ideas in general which appeared in Julia's talk. So we'll try to see them from a different point of view. I would like to start, first of all, with a theorem which already was presented by Daniel. And the theorem has many different avatars. So I will put a different version, and it seems like all these versions are unrelated to each other, but they are. And this is the theorem of Roth, okay, on arithmetic progressions, and I will just put a different statement. So for every alpha positive, there is some integer n, 0, which depends on alpha, such that for every finite group, abelian. Let's just make it simple, of odd order and G, and every A subset of G of density. The densities is going to be this relative proportion alpha, then A contains a non-trivial. I will drop this non-trivial 3AP. So a 3AP, we've already seen it before, is A plus D, A plus 2D, and all these three elements, they should all be in A, and D should not be 0. Okay, so this is the version that I will stick to it, and as actually most of the time, I mean, there are methods using Fourier analysis to.
What did you use N0?
Sorry, indeed. Oof, okay, such that for G with cardinality of G larger than N0, sorry, yes, so G has to be, sorry, yes, thanks. Right, so there are different ways to prove this theorem, often there is a kind of what's called a density increment argument, which it means that you have to do some kind of pass into a smaller subgroup. So it is nice if you get subgroups, and this is where most of the time, for example, the uniformity that Julia was talking about, it's very nice because it allows to produce a certain subgroup, and then you look at the distribution within that subgroup or the cosets in that subgroup, okay? Now, often that means that you have to pass to the group of characters, that Anand already mentioned, and so there is another theorem which allows to somehow do not have to use these characters that often. I will put it on the other side. So, and this is this theorem of almost periodicity due to crude sysask, and I would only put it for vector spaces over finite fields, okay, which is the example that appeared most of the time during Julia's talk. We're only going to be looking at FP to the end, okay? So what it says is the following. If you have, there is some constant, which is positive, such that for every odd prime, P and A and B subsets of FP to the n. So this is going to be the group where we'll be working all the time, okay, with A over G equals to alpha, some value, given epsilon, there is some subgroup, or subspace, I should say, maybe H or V, yeah, I guess subspace, V of Fp to the n of codimension bounded at some polynomial on 1 over epsilon, okay? It's just a bound, and the bound is quite explicit, such that I'm going to write something. A star B, x plus V minus A star B of x norm P is just bounded by Jesus, okay? So you see that someone is not a combinatorialist because they don't write this. They just say something. And it looks so much better, but I'd rather write it everything plus epsilon square half. Okay, it says if you take the P norm of a particular convolution, and I'm going to say what a convolution is right now, and then you compare it, what happens with this function when you move, okay, for x in Fpn and V in this subspace, okay? So if you compare these two values, they are quite close. Somehow, of course, given all the data that you are considering, okay? So the value of this function and the value of the function when you translate by V, they do not differ much. It's a P norm. Yes.
And G is Fp to the n.
Where did I put G?
Density.
Sorry, yes. Sorry. Yes. Yes, okay. So now, for G finite abelian group, what is A star B of x? Is actually, you run over all possibilities to write X as a sum of an element in A and an element in B. Okay, so this is what this is measuring, and so at the end of the day, it's actually the cardinality of, or the density, so to say, of this. Okay, so what this theorem they are saying is that somehow, if you look at the way that this intersection, I mean, we're normalizing, so we're looking at the way that A intersects X minus B, and we look at now the way that A intersects not X minus B, but X plus V minus B. So we're just shifting slightly the intersection, or I mean, or at least the concept that not the concept, the translate that we're interested. As long as we remain in the subspace that we found, actually these two values are very, very, very similar. Okay, so and the advantage of the almost periodicity is that it allows, first of all, to reduce many of the arguments, which are done usually passing to the using characters and using the uniformity of the Fourier, or I mean using the Fourier transform, and there is a way, hopefully, if I didn't copy it wrongly. So in particular, using that theorem, it is possible to deduce that the number of 3 APs in A, trivial or not, okay, so there are, the trivial ones are A, so A plus 0 and A plus 2, 0, okay? So this is just gonna be exponential of minus C alpha inverse log 2 alpha to the C times A squared. So of course there are many possibilities given by the element. Every element in A gives us a trivial 3 arithmetic progression. But if we manage that this value is not that small at the moment, it will say, so in particular, take n0 to be such that log of n0 divided by log of n0 to the C is larger than 1 over alpha. Okay, so this is, yes?
The C doesn't appear. Is it n bigger equal to C, or is it bigger equal to C?
So the C, sorry, the C appears in the code I mentioned, actually, sorry. Okay, so, yes, sorry. Right, sure. I have the impression that it is the case, yes. I mean, at least the way that I've phrased it. I mean, there are versions of the almost periodicity where you're not interested in getting a group, but you're interested in getting a Bohr set, and then somehow, but for the group version that I stated, the P seems to be the FP, the P of the, yeah. There are ways to compare the different norms, so probably at the end of the day you may be able to go from one norm to the other one, but at least the version that I stated is as such. I mean, I think, yeah. So, right. I mean, this is just a theorem coming from additive combinatorics, and so at the end of the day, so basically, so what it says is that A intersected X plus V minus B, it's similar to A intersected X minus B divided by G. Okay, so this is what the idea. The moral idea is that somehow it doesn't really matter that much. If we go, instead of looking at that intersection, we look at a different intersection, and then somehow things become a bit more structured by doing so. So, right. I should also say, I was commanded to do so. So there is work done by Anand Pillai and Gabe Conant on, I'm kidding. No, actually I had it written down. So there is a way which is actually very interesting, that if you have if you look at now not FP to the n, but if you look at an amenable group, okay, there is a way to somehow use the fact that this convolution product is always going to be a stable function in the sense of continuous logic, to deduce a non-quantitative version in this particular setup. So we're going to be looking at, or they look at an amenable group, and then they use the fact that the convolution is going to be a stable function, and then for stable functions, what they have is a very similar statement. It's not a subspace, it's going to be not a subspace, it's going to be a Bohr set, and then maybe there are some irregular situations that you need to, there are some bad cosets that you need to forgive or forget, but at the end of the day, there is a way to get a non-quantitative version of this theorem using continuous logic, right? And I think this is very interesting, but we didn't do that, and we will not do that. Sorry, Tai. So yes. So we the goal for us is to present a classical first-order logic version of that theorem, and then try to see how using that we'll be able to get this or that. I mean, something like this. Okay. So and as I guess, so this is the goal. Goal is goal. Really. That's the goal for today. Okay, so so the goal is to give a model classical or a model theoretic version of the almost periodicity resolved using in classical first order logic and deduce, using model theory, a version of Roth. Okay, so a non-quantitative version of Roth, I should say, maybe. Okay, so this is the goal, and then one of the classical, this is the non-standard yoga that you were saying. I mean, the idea will be like one starts. So what's the idea? I mean, or the setting. I mean, we consider a sequence of counterexamples to Roth's theorem, so a sequence Gn and n of counterexamples. Yes? That, so by non-quant, I mean, like, we will never get such a thing. Yes, I mean, but I mean, somehow these two things are very related, actually. If you're able to show that there exists, I learned recently, if you're able to show that there exists one non-trivial arithmetic progression, there are ways to produce many. So somehow these two statements are intrinsically related. And we will not be able to get any kind of statement of this form that tells us, I mean, okay, maybe we don't know. Sorry, maybe Daniel knows and I don't. But it seems for us very complicated because, I mean, there is proving Roth using this. There is a very intricate argument that it's maybe not that easy for us to somehow get a. Right. Where was I? Yeah, counterexamples, okay, with Gn plus 1 larger than Gn. Okay, so we're assuming this is not the case. We're going to get quantifiers. There's going to be some information which is fixed. And then every time we're getting larger and larger groups, these groups are finite, abelian, of odd order, and the cardinalities are getting larger. Okay, so then take now U, a non-principal ultrafilter. I'm spelling out many things that just appeared in Anand's and I mean, so this is, if you know already, this is maybe not that surprising. And then now consider G, the pseudo-finite group given by the ultra product. Okay, so then now this is going to be a pseudo-finite group with all structure. By this, I mean in the sense of non-standard analysis. Okay, so I mean by this that everything was named. We don't need this, but it's simpler. Okay, so G, every Gn, every single subset of Gn happens to be definable. Okay, and then we're just going on. We don't care about countability issues of the language so far. So, but there is a way actually to make everything much countable. So, yeah, and right. So, and now we can define actually because we have a pseudo finite structure. We can define the lob measures, right? So, if you have X, which is a subset of G to the M, internal or definable, it doesn't, I mean, internal or definable, it's the same two words. Then we can define the measure just to be the limit along the ultrafilter. I mean, we're just going to look at X in GMN. Hopefully it makes sense what I mean by this. And then we'll normalize. Okay, and by this I mean the trace of the set X in the particular finite group given by Gn or in the Cartesian product, okay? And then we'll just consider this, and then now because of compactness, this is actually a real number, okay? It's a number between 0 and 1, okay? If you, just because I'm taking it according to the ultrafilter. Right, so this measure, or these measures, so to say, okay, so how does it go? I guess maybe the second one would be good. Let's try. Second one. No, I have to. Oh no. Right. So I should have done the first one. Yes. No, this is a very asymmetric statement that is actually only related to the size of A. Yes. Wait, I'm a bit, yes. Say again. So, I mean, the B appears here, right? So if you do not control the B, then this value is somehow there. But at the end of the day, you'll apply it to A and A or A to A. So, I mean, it's related to A. But yeah, right. So this sequence of measures, sequence of measures are Kistler measures, each one of them, invariant under the action of the group, invariant under the group action, and they satisfy Fubini. Just because the cardinality does, they satisfy Fubini, okay? So, and because we put everything in the language, or every subset is definable, so somehow, definable, I should maybe say, definable Kistler measures, right? So it is a way, there is a way to talk using internal or definable sets about the fact that a certain definable set has measured at least something, okay? So, right, okay, very good. Okay, and then, which already appeared in the proof, or in one of the slides, in the talk of Anand, is that there is actually a very interesting result in this general setup. So we are not working in, we don't know anything about the theory of G. G can have a very wild theory. Most likely it's not simple, nothing, right? But still, Khrushchevsky managed, seems like it just happened. I mean, I'm sure he had a very clear idea how to do that. So he was able to show the following. So given A and B definable sets, subsets of G, and are any number, I'm just putting a very basic relation. So the relation X is related to Y if and only if the measure of X plus A intersected Y plus B is equal to R is a type definable stable relation, okay? Which this is a bit what you were mentioning about the fact that in super simple theories, I'll mention this later on. I mean, there is a certain stability still present even in a simple theory. Okay, so here we don't have a simple theory yet. There are some relations which are stable. What is stable means, just to avoid any confusion with K-stability, so it's just there is no, but it's actually because it's type definable, it will be the case. So there is no indiscernible sequence such that AN is related to BM if and only if N is less than M. Okay? So, and this can be done even if the relation is not type definable, even if it's just invariant. So this fact, Hrushevsky proved it actually studying the space of measures, and somehow looking at the extremal points in order to use a very important result in measure theory, in functional analysis, which is the Krein-Milnant theorem. It seems he, or someone pointed out, or he realized himself that actually there is a way to recover the stability, because this can be seen as just the fact that certain sets, or the what is it called? Not the scalar product, the inner product of two sets is gonna be seen in a particular Hilbert space is actually a stable relation from the point of view of continuous logic. Okay, so there is a way to actually use these without being in the setup that I'm just mentioning, just by working in continuous logic. But I would stick to this result. Okay, so this is the one that I'm interested. And did I want to say something more? Right. Yeah. Another remark is that so there has been in the past, recent past, lots of work done on stable relations which happen to be definable, and then there is a way to produce a stable regularity lemma, which will then produce a group using actually, for example, from the point of view of model theory, using actually local stability. Okay, but this only happens if the relation is definable. Okay, so if we have a function n equivariant, etc., etc. But if we start with a relation which is not going to be definable, which is the case here, it's very unlikely that the measures have a jump, right? I mean, so probably you have in order to be able to say that it's equal to R, you will need to be using that it's larger than every rational number, which is smaller than R, and something, right? No? And so we will not be able to use local stability to get the results that we're interested, yet we were able to prove a result which is the following. If S is M invariant, any subset, which is also, I guess M is a countable, let's just make it countable. Countable structure, S is M invariant, and the relation X related to Y if and only if the product happens to be in S, which
What's the context here?
the setting.
G.
Yeah. Countable element submodel, elementary substructure submodel. Yeah, so M is a countable submodel of G. Okay.
Who is S?
S is an M invariant relation. S is an M invariant set in G. I guess the way that I've defined it, yes. Okay. And now we're going to define a relation.
But it took a very rich structure, yes? So what about the existence of countable?
The language is uncountable.
Yeah, so I mean, I said there is a way actually to take care of the uncountability, that naming all the subsets seems to be increasing but there is a way to actually encode the power set as a new sort, and then somehow you use this in order to name every subset without increasing the language. Okay, so there are countable substructures. This G is Aleph 1 saturated, so that's why it's good to work with Aleph 0 to countable structures. So if you have a subset which is going to be invariant, any subset, and then we define a relation by saying x times y belongs to S, then so S is up to measure 0 a union of classes of G00M. Okay, and I'm putting two zeros because we are not in a simple theory. So I mean, and G00M is the smallest type definable subgroup over M of bounded index. Okay? So, and then in particular, which one is that?
You mean the relation x related to y is
Yeah, sorry, yes, sorry. The collection of pairs such that x is related to y. I mean, all the pairs, sorry, yes. Wait a second, what am I doing? Okay, now I'm confused. Okay, this one. But I want to go back to the fact of Khrushchevsky immediately to see what it says about. Wow. This is second. Okay. Gee, okay. So it doesn't matter. Ignore this statement. I'll just write something. In particular, and this is what I don't want to think about it. In particular, if the measure of A intersected C plus B is equal to some value R, and the type of C over M is dense, and now I don't want to fight, what is it called? Wide, weakly random, choose your word, okay? I don't want to fight. Choose the one that you like best, okay? Right, so it means, i.e., if C is in X and this is M-definable, then the measure of X is positive, okay? Then measure of A intersected D plus B will be also equal to R if D belongs to this particular coset and the type of D over M is dense. Okay, so this is what I want to say. Hopefully now maybe it's a bit clearer what I meant with this. Maybe not. So if not, ignore it. But we have a bit more general result. So okay. A and B are two definable sets, as seen before. Okay, so A and B. Sorry, Itai. Sorry, I should pay more attention, especially. Yes, you're right. A and B are M definable sets. So right. So how do we prove this result? Okay, and so if you think about what this result is saying, it's very similar to actually, if we have this in mind, okay, so this, we're now going to be seeing it as the measure of A intersected X plus B minus B, and this is now going to be the measure of A intersected X minus B. And so now you see that actually this result is similar. I mean, it captures kind of the idea that these two values are very, very related whenever we move X within a particular coset of a finite dimension. And here our best candidate is going to be G00M. Ignore this sentence. Is it okay? Is this okay? Okay, so good. Theorem, NP, Palacine, okay, and then I don't want to. Yes? Sorry? Oh, sorry. Okay, okay. So, good. So, what was it again? 2, okay. So, ignore it. I know in 10 minutes, someone's going to come again. Yeah, but what do you mean by ignore it, okay? I should have read our own paper, I guess. This also helps in general. So, right. Actually, we're very proud of this result. We're very proud, and I think I'm also particularly ashamed about this. So this happened at a moment that we were so what's the key ingredient is, by now you know what I mean, the proof of PQR by Anand, Tom, and Frank. Okay, so I don't mean the theorem, I mean the proof. Okay, so I remember meeting at a coffee place, right? I mean, I think this is the lowest time of my life, I think somehow. I became a nerd. I embrace it. I mean, we were having some kind of social interaction, supposed to, and then I just remember I stormed into the coffee place and I sat and I was like, and Daniel was talking, yeah, so Saturday I did it. I was like, oh, can we stop talking? And then so I was like, let's do math, okay? And then we just threw away everything. We started doing mathematics. I mean, everyone was looking at us like, and yeah, so I think this is, but we were very obsessed with the proof of this result. This is a proof that actually has been accompanying me for a very long time. I was a student in Urbana, and then I remember at the moment I went to, I read this paper, and I thought this paper was amazing. I mean, like there was lots of ideas, and I thought it was very nice. I had the feeling I could understand the arguments. I didn't understand the proof, okay? And then there is a moment in the proof it says, we may assume, and then something happens, you don't know why, and then, so I remember going to see Anand, and then I said like, I was actually thinking of like, should I try to do a theater? You know, like I would use a Spanish accent, a very strong Spanish accent, but then you're not gonna notice that I'm actually trying to interpret, like to play myself 20 years ago. You're gonna think like he talks like always, so then I'd be upset. Let's not do that. Anyway, so I asked Anand, and then Anand took it, and then he started chewing on the pen, and then he was like, expletive, beep, 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 right? I mean, like lots of expletives, some with F, others, and then he kept on saying like, what did he do? What did he do? So Tom is chairing, so I don't want to get upset with him. Can we assume that he meant someone else in the room? I mean, like, yeah, so, and then I thought at the moment I managed, like I understood it. I mean, really, this theorem became my theorem. Yesterday, I tried to explain it to someone, Julia, saying like, oh, we can do it, etc. I failed utterly and completely. Seriously, someone has a problem in this room, I think.
You start understand what we may assume. That's the point.
Yes.
In our paper, there's a proof of this.
Yes. It should be. Probably we say we may assume, as in the previous paper. I mean, actually the proof is okay. The proof is okay. It's just, why? Okay, I guess the question here is why? Why? I mean, like, why to the three of you? Like, why? Right? I mean, like, write details, first of all. I mean, just, it helps. Anyway, so it uses the independence theorem. The proof uses the independence theorem. And in the independence theorem, there is a relation due by non-forking, okay, due to, or saying relation x and y, or y and z, if and only if, saying phi of xy and psi of xz forks or doesn't fork, it doesn't matter, forks, is stable. Okay, and this is what makes the independence theorem work. Okay, so there is a certain relation which is stable. Okay, and then this.
Stable in this sense, right?
Yes, but it is all and so the idea is that you somehow take the reason why this proof uses this and that, and then you replace it by this, and anyway. The key ingredient, yes. I'm not telling you how, but I mean, if you just I mean, well, I don't know. If you think about it, then probably it's very simple, and then we'll be even more depressed, but it took us a long time, I mean, somehow. And yeah, and so the stability is used in the fact that some relation is going to be stationary. I mean, so that if you move, if x and y are independent, and if they satisfy the relation, if you move slightly x or y, and they are independent, they still will satisfy the relation. So this is kind of the idea, and then there's a lot of cancellation going on, which, I mean, how do you think about this cancellation is mysterious. But anyway, so, right, so now let's, okay, so we're gonna use this theorem, not a theorem, this theorem, okay, and then we're gonna try to prove Roth, okay, so this is the goal. I was told when I first arrived to Lyon, I was told, come into my office, okay? So I'm kind of used of this because I've already lived it with someone else, but I was told, like, please go into my office. So I was ushered into the office, and I stand there, and I thought someone is gonna say, your talk was amazing, and then the person said, oh, this was not a math talk, okay? A math talk should always have a proof, right? I mean, I seem to remember that someone told me, so there we go. We're gonna do a proof, okay? So, right. Which one should I do? I guess the first one. And then we're done. No, 3. Okay. Right. So let's try to do the proof. I don't know how to do this properly at all, okay? Like, not even if I try, so it doesn't matter. Usually my clothes look like, I look like Martin Ziegler, which is very not a compliment, but anyway. So, yes. Anyway, so let's try to prove corollary. So again, in the same setup, okay? So if G has finite two torsion, okay, which is gonna be the case if the group G has been constructed as a sequence of counterexamples, because we're only looking at groups of odd order, okay? So then at the end of the day, we're gonna get this situation, and it's abelian, okay? And a subset of G is dense. That means the measure of A is positive. Then the collection of pairs, x1, x2, in A times A, such that x1 plus x2 happens to be 2 times y, and y belongs to A, is dense. Dense, of course, means with respect to the mu2 measure, right? So the measure in two-dimensional space. And if you remember the way that Daniel was talking, a 3 arithmetic progression is actually just solving that equation, okay? So if we can solve an equation of this form where all the entries belong to A, then we have an arithmetic progression, okay? And then it's actually not gonna be trivial because we're gonna get x1 and x2, which are very far apart, and then somehow the value G or D, the distance, will not be 0. So I will not do that now. So, okay, 2 pages, okay. So the ingredients, what do you need to know in order to prove the result are the following. Sorry? But we'll need 4 things. And if we assume that we know these things, then the proof is very simple. So the first thing is Khrushchevsky stabilizer. Stabilizer will say, so M is going to be a countable structure, submodel. And so the first one says that if the type of, say, C over M is dense, and G belongs to G00 of M is also dense over M, then this partial type, or minus G, doesn't matter, is dense over Mg, okay?
Type C over M, what?
So if you have a type which is dense, over M, and we have an element of G00M which is also dense over M, okay, this partial type as a collection of formulae is also going to be dense over Mg. Yeah, of the type, okay?
Yeah, put some parentheses.
I can go. I don't know which parentheses should I put. I mean, and this is okay. So, right. Okay. So this is the first result. So in particular, really in particular now, in particular, there is C1 which has the same type as C over M, such that C1 plus G also has the same type as C over M, and C1 is dense over everything, M, G, C, whatever you want, okay? So this is the first, just because this partial type is dense, and the measures allow us to actually extend dense types to other parameters. The second condition is the fact that denseness, I mean, so we want to show that something has positive measures, so there is kind of a certain, so if this type is dense, and this type is dense, then this type is dense, and a 2 type is also dense. Okay? So I'll lift it up, okay. No. So this is A, this was B, C, D, E. Oh, okay. Oh. A plus B. So if you move A by things over which A is dense, it still remains dense. And if you and if you just consider the type of the pair, it's also going to be dense in the with the corresponding measure. And then I know. Okay, so C, so if the type of A over MB is dense, and the type of B over M is dense, no, but did I? Yeah, it doesn't matter. So it doesn't follow that the type of B over MA is dense. We don't have symmetry, which is really very annoying, okay? We don't have symmetry. In general, we cannot start flipping things around, but X, M definable, is dense if and only if it contains a random type. Okay, and a random type is just going to be a particular class of type. Random are dense. I don't want to say what random types are, but the advantage is that this will be true. So if you have type of A over MB, which is random, and the type of B over M is random, then the type of B over MA is also random, okay? And then D is that because G has finite 2 torsion, then type of A over M is dense or random, it doesn't matter, if and only if the type of 2A over M is random, okay? So we can multiply by 2, and then we preserve randomness. And now, yeah, I completely miscalculated the, anyway, so no proof. I still didn't manage, anyway. Yes, sorry. So how to prove Roth, okay? So the idea, it suffices to show that the measure of A intersected to A minus A is positive for some A in a random. If you're able to do that, you're done. Why? Because if this set it's a definable set, and if it has positive measure, it will have a random element, let's call it x1, and then you can subtract 2a or add it, whatever, and then you get the second coordinate to the equation x1. This will give rise to a pair like this, and x1 and x2 will be both random. Actually, one will be random over each other. The whole thing will be then dense, so we have dimension 2. I don't want to define it. It's actually, the good thing is that it's already been defined twice, by Khrushchevsky and by Pierre, and then they both say, we could define it, but it will be complicated, so we don't have to. Right? I mean, basically, yes. So, but for the definition of randomness, it's very important that actually we're working in a countable thing, because we use sigma additivity of the extension of the measure to a real sigma additive measure. So we need this, and basically the idea random, you need to avoid sets which are type definable and say the measure of the fiber is always 0. You need to avoid these kind of sets which become type definable. So it suffices to show this, and the idea is somehow find A and B suitable such that, first of all, the measure of A intersected A plus B minus A is positive, and A plus B is the class is equal to this class. And I'll stop here because so we're gonna find A and B, which are very nice, such that this has positive measure, okay? And now what we're gonna find is A and B are gonna be such that A plus B and the element 2A, they both happen to live in the same coset of G00. So now our result, where is it? I deleted it. No. Yes. Yes, that result, okay, will tell us that if this has positive measure, this one has positive measure, and then you can do this using A, B, C, and D. And I think it's a very good moment that I stop and apologize. Sorry.